Right, okay, I'm going to talk to you about representing vectors and the different ways that vectors are going to be represented. And I want to look at the vector 3, 4. So let's say, for example, I've got the vector A, which is the vector 3, 4. Now, we know what this means. We know that if we were to draw a set of coordinate axes with an x direction and a y direction, we understand that the vector 3, 4 is, if you start in any location, it's a movement of 3 units to the right and 4 units up the y-axis. So, of course, the vector 3, 4 would look like that. There is my little vector A, which is going along 3 units in an x direction and 4 units in a y direction. However, a vector like this can be represented in a different way, and it's all based on unit vectors. And unit vectors have a length or a magnitude of 1 unit. So I'm going to write that down. Unit vectors have a length, which we also call a magnitude, of 1 unit. And there are 2 really special unit vectors that are used. If I were to draw the coordinate axes, again, x and y, there is a unit vector that always runs parallel to the x-axis, which is 1 unit long. And we call that vector, little vector I, where I runs parallel to the x-axis and is 1 unit long, or 1 unit in length. Would look better written down. I've also got another really important unit vector, and that is the vector that runs vertically parallel to the y-axis. It also has a length of 1, and we call that little vector j. So I'm going to write down the fact that j runs parallel to the y-axis and is 1 unit in length. Now, because they are both unit vectors, and they are both really important because one is parallel to the x-axis and the other is parallel to the y-axis, we can actually write any 2-dimensional vector in terms of I and j. So, for example, if we look at vector A, which is 3, 4, well, the 3, which is running 3 units parallel to the x-axis, we can actually say that A is going 3 units to the right, or 3 times little vector I, and it's going up 4 lots of little vector j. This is called writing vector A in component form. It's made up of 2 components, which are the unit vectors I and j, and we can write any vector in component form using just I and j when, of course, we're talking in 2 dimensions. Okay, we were just talking about unit vectors I and j, and I was explaining that any 2-dimensional vector can be written using the 2 components I and j. So any 2-dimensional vector can be written in the form p lots of I plus q lots of j. And that's just a convention. And for example, if I had a vector going from A to B, for example, I'm just going to write B there, so the vector A to B, and B is going to C. Let's say that B to C is that vector there. If I wanted to write the vector A to C, I would have to go from A to B, and then I would have to go along B to C. Now, if I had the vector AB, which was, for example, 2 lots of I, then vector AC would be 2 lots of I, add whatever vector B to C was. Let's say B to Z was something like 1.5 lots of J. Well, A to C would be 2I plus 1.5J. We could also write that in column vector notation, which is 2 and 1.5. So any two-dimensional vector can be written in the form Pi plus Qj. I'm going to give you some example questions using component notation, and I'm going to tell you that little vector A is 3I minus 4J, and I'm going to tell you that little vector B is 2I add 7J. And what I would like you to do is I would like you to find the following. So A, can you find a half of A? B, can you find out what A plus B is? And C, can you work out what 3A subtract 2B is? You can write your answers in either column vector notation or component notation. You may pause the video while you do it, and I'm going to do the answers now below. Okay, so for part A, if I'm going to be writing down a half of A, well, that's going to be a half of 3I minus 4J. Well, that's going to be 3 over 2 lots of I minus 2J. It's absolutely fine to leave it in that form, but if you wish to, you can write it in column vector notation, and then it would be 3 over 2 and negative 2. So by writing it in those two different forms, we're getting used to seeing it written in two different ways. Vector A plus B, well, I'm going to have to add vector A, add that to vector B. So I'm going to add my I components together, so I can see I've got 5 lots of I, and I've got negative 4J, add 7J, and I've got 3 lots of J. If I wanted to, I can then write that in column vector notation as 5, 3, which would also be correct. Part C, I've got 3 lots of A, subtract 2 lots of B. I just want to be able to see what my vectors are there. Okay, so I've got 3 lots of A, 3I minus 4J, subtract 2 lots of B, and of course I've got my scalars here. I'm multiplying A by 3, so both the I and the J components get multiplied by 3. And if I'm subtracting 2B, both the I and the J components get multiplied by 2 before I do the subtraction. Keeping my brackets in there because that's really important. I don't want to go wrong. So I've got 9 lots of I minus 12 lots of J, subtract 4 lots of I, subtract 14 lots of J. I can see I've now got 5 lots of I, and I've got negative 26 lots of J. Absolutely fine to leave it in that form, but if I wish to, I've got 5 and negative 26 as my column vector, which is also correct. I'm going to do another example on the next page. Okay, example 2 asks me to draw a diagram to represent the vector negative 3I add j, and to write this as a column vector. Fairly easy kind of question, really. Just make sure that we start somewhere, and then I've got to go along negative 3 lots of I, and then up 1 lot of j. So I'm just going to draw that. I went negative 3 lots of I, and I went up 1 lot of j. I started from the bottom right hand dot, and I went up to the top left hand dot. So my actual diagram to represent that vector, let's just highlight the vector in question, is the vector that's there. If I want to write that as a column vector, that is the vector -3 and 1. Okay, example 3 has given me 3 vectors, little vector A, little vector B and little vector C. I've got to find out A plus B plus C. Now, of course, one thing that I could do, if I wanted to, is I could just write down all my vectors being added together. But as you'll notice, it's quite a lot to keep writing down I's and J's all the time. One of the problems I have with writing vectors in component form is that when some people's writing is difficult to read in the first place, the I's and J's can look very similar indeed. What I would suggest when you're writing out quite a few vectors is that it's absolutely fine if you want to turn them into column notation in order to add them or do whatever you want with them really. But I find writing them in column notation much easier to simply add them together there. I've got 14 take away 3, which is 11. And I've got 5 subtract 10, which is -5, add 9, which is 4 there. So I think A plus B plus C is 11, 4. But if it's required that I write it out in component notation, I'm going to translate that answer into my components of I and J. Therefore, both answers mean exactly the same thing, and I can work in column notation if it's easier. Example 4 is a slightly more tricky example. Having been given 2 vectors, A and B, I've got to now find lambda if A plus lambda B is parallel to the vector I. So I think what I'm going to start doing is write an expression for A, add lambda B, where lambda is just a scalar multiple of vector B. So I've got vector A, which I've got here, and I've now got to add lambda times vector B. Now, if I multiply all that out, well, I've got 2i, add 5j, and I've also got now 3 lots of lambda I minus lambda j. I can't really add an awful lot together, but I do know that all the i's can be written together. And then I do know that the j's should be written next. I can now factorise by seeing that I've got 2 add 3 lambda lots of I, and I've got 5 subtract lambda lots of j. Now, remembering that vector I runs parallel to the x-axis, I now know that if my vector is parallel to the vector I, then the vector component j should have a coefficient of 0. This means that 5 subtract lambda has to be worth 0, and therefore lambda is 5. What that means is my vector is running parallel to the x-axis, but it's not running at an angle. I hope that makes sense. I was distracted by my daughter walking in then. You are now free to go on to exercise 11b. And I suggest that if you feel fairly confident, start with question 4 and work onwards. If you want to do questions 1 to 3, please, by all means, do so. Thanks very much for listening. Bye-bye.